Hey, and welcome to the next video in my Functional Programming in Python series. So in this video, we're going to talk about parallel programming. How can you execute code and do data processing in parallel using Python and using functional programming principles? So in this video, we're going to take everything you've learned so far and use these techniques to very easily take some existing code and make it parallel so that it runs on all of your CPU cores at the same time, potentially reducing the amount of time it takes for your program to run. And I'm trying to do this with some very hands-on examples that build exactly on what you've seen in the previous videos. So what I've got here is a simple test bed that brings back our data structure here. So we've got this immutable data structure that represents a bunch of scientists that worked in different fields when they were born, their names, whether or not they won the Nobel Prize at some point. And then we've got a simple transformation here where we take each scientist and then create a transformed output data structure that contains the scientist's name and their age as of 2017. And all of this is going to look familiar. So at this point, you probably want to check out the first video in the series on how and why we set up this data structure the way it looks like here. And of course, also here it's about the name tuple. And then you probably also want to watch the video on the map function that showed you how we can take this scientist structure here and transform it into a new data structure. All right, so let's run this example because I think that's going to make it a little bit easier to follow. I save this as parallel pi. When I run this, you can see here, well, okay, we're just printing out the input data structure. It's a scientist thing here. And it looks like this. And then we're applying the transformation using the map function. And we're printing out the result. And this is the result that we get here. So we get all of the ages for these scientists and their names. Now, this transform function here is really simple, right? We're working with a relatively small amount of data here. And we're working with a simple transformation that doesn't take a lot of computations. And it will execute very fast. But if you imagine this was a more complex operation here, for example, if this needed to go out and fetch some data from the internet and then process it. So if it was IO bound, it was waiting for IO to complete, for that website fetch to complete. Or if this was doing some more extensive number crunching, then performing this map operation would actually take quite a while, right? Like if I run this right now, it's instantaneous. But if we needed to do something more complicated here, this would actually take longer. And just to simulate that, I'm going to make this transform function just a little bit slower. So we're just going to insert a time sleep call here. And we're just going to sleep for a second. And if I run this now, I can see here, this actually takes a little bit longer to process. We're still waiting for the results, and we can make this a little bit more interesting because I want it to be a little bit more verbose. I want to be able to see what's going on. So I'm just going to say processing record x.name, and that's going to give us some output as this processing is happening. And then we can say, done processing record x.name, and then we're going to return this result. So, I've made this function here a little bit more complex and also added some logging statements so that we can see what's going on. And now I can run this and I can trace how the data is being processed, right? So basically, this is now telling me how it is running this transformation. And I can see exactly what's going on. And I can see how these records are being processed in parallel. Now, you may be wondering, okay, why are we doing this, right? Like, it's kind of obvious, like, why do I even care about this? So the cool thing is, because we wrote our code in a functional programming style, we can actually parallelize it very easily because there is a parallel map construct we can use. And that way we can run these calculations, these processing steps that now happen sequentially, meaning one after another on a single CPU core. We can parallelize them and run many of them in parallel. And now that we have all of this stuff in place, this is very, very easy to do in Python. And this is what I'm going to show you in this video. So what I'm going to do next is I'm going to import the multiprocessing module because that has all of the building blocks that we need to actually run this operation in parallel. And before we move on, I want to extend this testbed a little bit more because I want to add some more logging so we can actually trace how long it took to calculate this result. So what I'm going to do here, I'm going to take the start time before we apply the map operation. And then I'm also going to measure the end time what time.time does, it just gives you a second space timestamp as a float. All right, so what we're going to do here is we're going to print the time to completion, and we're just going to calculate that as end minus start. And that's going to give me the float in seconds that it took to run this piece of code here. So now when I save this, we can run this again. It's going to very slowly process all of these records one by one. We're simulating here that this would take up to 1 second. And then it's printing out, okay, this took 7 seconds and a little bit more, which makes sense because we have 7 records in here. And I'm just going to polish that a little bit more just to make sure we have this nicely formatted. So I can use a format string here and then run this again, do our timing. So now we get the input data, we get the processing as it happens. This is logging some stuff, and it tells us, hey, it took this long to calculate the result. And here it is in seconds. And, we can make this a little bit more nice. Just, limit it to 2 decimals and just have a really nice output. And I often like to build stuff like that if I'm experimenting with something. And it really helps me get what I want from these experiments and from these analyses. All right, so now we've got everything we need here. We've got the strictly sequential implementation of this program here. We already also imported the multiprocessing library. So what I'm going to do now, we're going to replace the sequential step here. We're going to replace it with some multiprocessing code. So what we need to do here first is we need to create a multiprocessing.Pool object. And we need to store that somewhere. So a multiprocessing pool is basically an interface that we can use to run our transformation or our transform function on this input data in parallel, spread out across multiple CPU cores. So this pool instance, it has a map function. And I can say, okay, we're going to map the transform function over the scientists, and this is our result. So this corresponds exactly to the sequential map function call here. I'm just going to clean it up a little bit and maybe bump up the font size again for you to see. And now if we run this, what do you think is going to happen? So remember before, this took about 7 seconds to execute. And if we run this again now, well, we're getting a way different output, right? It looks like we're actually starting the processing here for 4 records all at once, and then they all complete as a batch of 4. And we have another 3. I guess that's the remaining ones. And then those complete as well. We get the same result, but we get it a lot faster. Previously, it took us 7 seconds. Now we did it in 2 seconds. And that happens because, well, we have these 2 batches here, essentially. Now, what is going on here? So this is the magic of the multiprocessing pool. Because what it does is it actually fans out. It actually creates multiple Python processes in the background. And it's going to spread out this computation for us across these different CPU cores. So they're all going to happen in parallel. And we don't have to do anything. The result we get is exactly the same. The multiprocessing pool fans out and does all these computations for us, applies the transform function, and then brings back the results and assembles this output data structure here. So we get exactly the same result here, which is pretty cool. Now, there's a couple more parameters we can tweak here, and I really want to make sure that you see what's going on behind the scenes here. So the first thing we're going to do is we're going to add some more logging to this transform function so we can see what's going on behind the scenes. And for that, I'm going to import the OS module. And then here, we can print out the process number, some identifier for the current process. And we can do that with the os.getPID function. So we can say process, the name of the process is working on this record. And then we can say process, get process ID, done processing record. And now if I run this again, we're going to get some more extensive output here. So each process that happens in parallel, it gets a unique identification number. And we can see here how the multiprocessing pool spreads out our computations across multiple cores. So what you can see here is that we have these 4 processes, 17, 3, 24 to 27. And they're working on stuff in parallel. And then they're being reused. So in the second batch, the same processes, again, are working on other data. And we can influence this behavior. So we can actually put a limit and say, well, I only want 1 process in this pool here. And when I run this again, you can see here, well, now we have a single process that's doing all of the computations. And again, we're going to end up with a 7-second runtime. And if you look at the log here, you can see exactly that's the same process processing each record one by one. And there's no parallel computation happening. And now if I crank this up, I can say, well, we want 2 processes. And now if we run this again, we have 2 processes working in parallel, and they're processing these records in parallel. And now we get a little bit of a speed up. And of course I can go crazy here, and I can actually say, okay, I want a process for each record here. So I want the number of processes should be the number of records in this thing here. And that way we can process all of them in parallel, and we can really cut down our time to complete to a second, which is about as long as it should take to process a single element. And, of course, this is a bit of an academic example or just a toy example because, well, we're just sleeping here. So there's really, nothing very interesting going on. But if you imagine this was a call that was waiting on I/O, or it was waiting for a website download to complete, if this was a web scraper of sorts, you could do all of these things in parallel. And with the multiprocessing pool, you can really influence how these operations are performed across multiple CPUs or multiple CPU cores, and you have a lot of flexibility in configuring it. There's other options here. For example, we could say, okay, I want 2 processes, and there's another setting that's called max tasks per child. And I can say, well, I want 2 processes in parallel, and I want the process to restart after it has completed a number of tasks. So if you run this, we're going to get a slightly different output here. So again, if we look at the process ID, you can see here, okay, we're starting out with 03, 04, and those are doing some processing. And then we're getting 2 brand new processes that are processing the next elements. And then we're getting 2 brand new processes again, and so on. So with the multiprocessing pool, you can really influence how it's distributing your calculations across multiple CPU cores. And of course, you can also leave out these settings. And what it's going to do then, it's going to spawn as many processes as you have CPU cores. So I'm on a dual core with hyperthreading machine that Python sees as a quad core CPU. And that means it's going to spawn 4 separate processes to maximize the CPU that I have available. I just love this way of parallel programming because it is very easy to do. If you write your code in a functional programming style, and if you're using a map function, then it's very easy to parallelize this code, as you've seen here, right? I didn't change anything here, really. I mean, we made some cosmetic changes just to be able to trace what's going on with this transform function. But really, all I did was change these 2 lines of code. And now all of a sudden, these calculations are running in parallel across multiple CPU cores. And I think that's a really powerful concept. Now, there's more to this, of course. This is more, this is really just scratching the surface. But I hope it is enough for you to see the value that this programming model brings with it. And I really want to encourage you with this video to go out and do your own experimentation, right? Maybe turn this into a little web scraper. Maybe you can do some I/O or some more expensive computations here, and then use the same technique to speed this up and actually get your result a lot faster. If you imagine you had to fetch 10,000 websites, well, if you did that sequentially, this could take a really long time. But if you can parallelize them and fetch these websites in batches of 100 items at a time, then you're going to get a huge speed up. It will be relatively easy to do this with the multiprocessing pool module that's built into Python. So yeah, give this a shot, play with it, get familiar with it. All right, talk to you soon.